The European Learn project brings together 12 partners from across Europe to study indoor air quality and its effects on children's health. We know that air quality affects respiratory health and long-term well-being. But in order to improve the air quality, we first need to monitor it and measure it. And that is what this project is about. Most air quality sensors today measure relatively large particles. This is called PM10 or PM2.5, for instance. But there's a whole class of much smaller particles that these sensors simply cannot see, ultrafine particles or UFPs, smaller than 100 nanometers. These particles are a growing concern because their tiny size allows them to penetrate deep into the lungs and even enter the bloodstream. Yet we have very limited data on UFP levels in the environment where we spend most of our time, homes, offices and schools. The equipment that can actually measure these ultrafine particles are, for instance, the scanning mobility particle sizer (SMPS) system, a very expensive and bulky equipment that also uses harmful liquids that it releases into the environment. So this type of equipment is not really meant for use in a classroom or in a public environment. This is just for a lab environment. So it is really, if we want to do this monitoring on a larger scale, we really need a simpler, cheaper solution to measure these ultrafine particles. At TU Eindhoven, in the group of Andrea Fiore in the physics department, a completely new detection principle has been developed. A nanophotonic sensor integrated on the tip of an optical fiber. This tiny sensor, smaller than the cross-section of a human hair, can detect individual nanoparticles by measuring how they shift the optical resonance of a photonic crystal cavity. No condensation, no butanol, no moving parts, just light and physics. We have already demonstrated that this sensor can detect single particles as small as 50 nanometers in a liquid.
To detect the particles inside these droplets, we are using a new detection technique using photonic crystal cavities. To put these photonic crystal cavities on top of the fiber, we are using this experimental setup right here. At the heart of our sensor is a photonic crystal cavity, fabricated from indium phosphide and transferred onto the tip of an optical fiber. Next, we send laser light through the fiber, and the reflected signal is collected. The photonic crystal acts as a very precise optical resonator. It is very sensitive to particles entering the detection region. When a nanoparticle gets into the detection region, near the cavity, it slightly changes the local refractive index, which shifts the resonance wavelength. Each particle produces a tiny but measurable step in the signal. The next milestone of this detection scheme is to use it on a droplet that has been transported on a PCB.
Our answer is a three-stage approach. In stage 1, we capture the ultrafine particles into a droplet using a combination of inertial forces and electrostatic forces. In stage 2, we transport the droplet from the capture region to the detection region using a technique called electrowetting on dielectric, EVOT. In stage 3, we detect the particles inside the droplet using our optical fiber tip sensor.
So now that by using SMPS system, we can have the concentration of ultrafine particles in the air, we are going to accelerate that ultrafine particle into a droplet sitting on this printed circuit boards or the impactors. So the larger particles, due to having enough inertia, they can impact the droplet. But what about the smaller particles like ultrafine particles, which are smaller than 100 nanometer? That's where the electrostatic force comes in. But for using electrostatic forces to direct and manipulate these ultrafine particles, we first need to charge these particles. And for that purpose, we need to use DC Cournot dischargers. And for doing that, we need to build up a high DC voltage setup.
Once the particles are captured in the droplet needs to be transported to the sensing area. We do this by using an effect called the electrowetting, which is basically a droplet sitting on a hydrophobic layer, sitting on a dielectric, which eventually has an array of electrodes underneath. By applying sequentially voltage to these electrodes, we can change the contact angle of the droplet just slightly enough so the droplet starts to move. And this is how it works.
So this is our three-stage approach: concentration, transport, and detection. We have demonstrated each of these stages separately. Now our challenge is to combine them all together, integrated on a single PCB into a single device. The LEARN project is coming to an end, but here at TU Eindhoven we will keep working on solving this challenge. Our final goal is to create a low-cost, portable solution that can be used to monitor ultrafine particles in environments such as schools and other public places. This will provide new insight about ultrafine particles in the air and their effect on our health.